I think it's time to get started. I will check my watch again here. Yeah, we're right. Actually, I'm about a minute late. I'll begin. Dear Heavenly Father, we thank you for this day again. I thank you for these students. Just ask you to bless our work today. Help us to glorify you what we do. Help us to just understand your creation a little bit more. In your name I pray, Lord Jesus. Amen. All right, so let me talk to you guys a little bit more about vectors. And somebody asked me before class, are we ever going to get back to calculus? And the answer to that is, of course, yes. However, the good news is also that pretty much the vectors will never leave us. So that's very good news, yes, because vectors are amazing. Okay, so just to recap, we can take any vector, and this is a lie, so you tell me why it's a lie, and write it as a hat. Where a is the square root of a dot a, right? Why is this a lie? Part of it's a lie. This is always true. That's true. This is not always true. When is this not true? Just one case. Zero vector, right? Zero, we can't write a unit vector in the zero direction. Okay, so that's for non-zero vectors, admittedly. And we worked on understanding this thing last time, right? A dot B is equal to, and I'll write it in 3 dimensions because usually we're in 3 dimensions. And, you know, if you can do 3 dimensions, you can drop back to 2, right? Right? So this was the dot product. And if that was all that it was, it would be kind of a quirky, oh, look at that. You can calculate the length of the vector by taking the dot product with itself and taking the square root. Isn't that quaint, right? But it's more than that, because we found a theorem last time that this is equal to AB times the cosine of the angle between the vectors. And that equation, that equality I just wrote, is the law of cosines. All right, that's the law of cosines in vector formalism, which means it gives you access to solving non-right triangle trigonometry whenever you confront it if you just simply use the language of vectors. Now there's a subset of you who spent more time on Minecraft than others, and you have a well-developed understanding of coordinates, right? And so you're like, I don't need vectors because I can just hang a point in space and then calculate height, width, depth off that point, and I can do everything with points and planes and right triangle trigonometry and a suitable collection of triangles. Prove me wrong. I can't prove you wrong, you're right. But a lot of people don't have that geometric insight because they were playing Candy Crush, I guess. It's part of my brother's problem. He believes in algebraic solutions to everything. It's no accident. All he plays on his phone, Candy Crush, all the time. Anyway, so I have 2 little brothers. I'm talking about the one who's a math professor. Anyway, so this is the dot product. Now, we should talk about what does it mean when a dot b is equal to 0? This means what? A is perpendicular to b. All right, great. What does it mean if we have a is equal to some constant times b? Where c is just a real constant. What do we say about this? So here, and I'm assuming that the constant is positive, okay? For a positive, real positive constant, this is one way you could define a parallel to b, right? Now, if this is the definition of parallel, how are the unit vectors of a and b related for parallel vectors? What? They're equal, right? So you could see that this is the same as saying a hat equals to b hat, right? And so at the moment I wrote that, I need to put all of this in a box. So I'm assuming what? This is all for a, b, not equal to 0, right? Is there any other characterization you could give me of parallel vectors? How about this? Theta equals to what? Inverse cosine of what? A dot B over AB, right? If we solve the formula up here for theta, that's what we get, yeah? And that has to equal what if A and B are parallel? How does that A dot B over AB simplify? It's not 0.
1?
Yeah, it's 1, right? So this would become, I'll just write out inverse cosine. I mean, pick your poison. I'll do the original one. So we have, you know, A dot CA over, you know, length of A, length of CA. And that simplifies to 1 because we're assuming C is what? Positive. If C was not positive, it wouldn't simplify to 1, it would simplify to minus 1. Right? But because C is positive, that simplifies to 1. So we get inverse cosine of 1, which is also known as 0, right? So yeah, I mean, you could have told me that at the, somebody probably would have told me that at the start if I had waited long enough to hear you, right? You would have told me that parallel vectors are those vectors that have 0 degrees between them as angles, right? If I draw a picture of two parallel vectors, like this and like this, what's the angle between them? Well, it's hard to see, but theta is equal to 0 degrees, right? You're like, no, it's 0 radians. So, okay, fine, we agree, right? Now, some of you are itching to do calculus. It will become important that we think of sine and cosine in terms of radians when we get to that, right? But personally, I think of geometry in terms of degrees. It's how I was raised, what can I tell you? All right, what would it mean if A is equal to CB, but C is negative? What would we say then? A and B are what?
They go in opposite directions.
They're going opposite directions. And the term we have for that is anti-parallel. But just like you said, they go in opposite directions, absolutely. And in that case, we would have what? Theta equals to 180 degrees, right? Like 180 degrees opposed. Or pi radians if you like. Okay? If you want to capture both of these ideas at once, right? So if you put these two things together, theorem, if you like, A dot B is equal to plus or minus AB if A and B are either parallel or anti-parallel. I just want to talk about all this stuff at once because as a student it frustrated me because sometimes people will be like talking about parallel, sometimes people talk about anti-parallel. What's the other thing people talk about with regard to vectors in their common direction? Orthogonal, perpendicular, yep, that's true. Right here. We'll get back to that though. Good. But what word do we have to talk about parallel and anti-parallel at once in one foul swoop? This together, parallel or anti-parallel, we call such vectors collinear. Collinear vectors are vectors which lie along a line. So if you want me to draw a picture of that, it's pretty simple. There's a line. Here's a vector along the line, right? So to have a collinear vector, you can either have something that's like this, right? Or you could have something like that. Either way you slice it, those are collinear vectors to A. All right? Please don't ask me today if 0 is collinear to other vectors. I just don't remember. So I think it might depend on which side of the bed you get up in the morning or something. But all right. So there you go. This is, in a nutshell, how we can judge parallel, perpendicular, right? Just one silly little example before we get into the meat of today's lecture. Example 1. This is oftentimes a test question I ask. So like find B of length 42 in direction of A equals to, oh, I don't know, -1, 2, -2. So how would you do that? I have planned poorly. I know I must erase my glorious 0-degree picture and my collinear picture, but you can forgive me, yeah? Am I okay?
If you find the unit vector of A multiplied by the magnitude of B.
I don't know. Yep. Yeah, you can do that. Absolutely. Yeah, that's actually how I'd solve the problem. What's the other way people were thinking about doing it, though? You could do what? You could just say B is equal to, C times A, and then put the length of C times A equals to 42, and then solve for C. And then you get 42. So yeah, because it's in the direction of A, which means it's parallel to A, which means the C should be positive, But yeah, that's how I do it. I just say A hat equals to, what's the length of A here? Can you guys tell me? We got 1 squared plus 2 squared plus 2 squared, otherwise known as 9. Square root of 9 is 3. So that's a length 3 vector. So that's A hat. And then B is equal to 42 A hat. I would say that's by geometric intuition. That's where that step is coming from, right? It shouldn't be discounted. And anyway, so there you go, 42 over 3. -1, 2, -2. What's 42 over 3? 14, yeah? So we've got 14 times -1, 2, -2, also known as -14, 28, -28. And there you go, there's your answer. I like this example because it's a nice, simple example to start with. I often choose poorly and give you a complicated example to start. But this is not that. The other nice thing about this example is it shows you the utility in resisting the urge to bring that third inside just because you can. Right? See the payoff of not writing this in terms of 3 fractions? You didn't have to cancel 3 fractions, you just got to cancel the 43 over 2, which is like way easier, right? All right, so let's go on. So here's the next question. Given A and B non-zero, how can we find, say, a vector C which is perpendicular to both A and B? Okay, I'll allow it. So you're like, I hear people saying cross product. I would remind the others of you who are not taking my physics that they have an unfair advantage over you. But life isn't fair, right? So anyone who says differently is selling something, right? Somebody said that once upon a time. So of course, if you want to think about it geometrically, you can kind of, if you got some markers lying around, you think here's one vector, right? And here's another vector, right? And so if these two vectors are in some plane, right? The third vector we're looking for, which is perpendicular, I can't say perpendicular. perpendicular to these two, right? Should be like this, right? Or what? What else is perpendicular to both this and the red and the blue vector?
The negative.
Yeah, the other way around, right? So obviously there's some kind of ad hoc choice that has to be made in that. And it's worse than that too, right? Because why is it a length 2? Why couldn't it be, length 3? That's still perpendicular, right? Or length 4, still perpendicular, right? So this question alone that I've phrased, being perpendicular to two given vectors, does not uniquely fix a third vector in 3 dimensions, right? So we need also such that we're going to have to choose an upside, right? So if you picture, this is, let's say this is A and this is B in some plane, right? We're going to have to choose an upside. And the way we're going to do that is with what's called the right-hand rule. All right? So watch me. We take our right hand, we point them in the direction of A, right? Point your fingers in the direction of A, and then you cross your fingers in the direction of B. Whatever side your thumb is forced to point, that's defined to be up. That's the right-hand rule, just that. So it's helpful to have something that's like a plane to demonstrate this on. So here's a plane, right, the book. So I take my right hand, point it in I'm saying the green direction, right? You guys see me? And then I cross my fingers into the red direction. My thumb has to point up, right? On the other hand, if I start in the red one, I point my right hand in the direction of the red one, I have to turn my hand over if I'm going to curl this way, right? Can any of you bend your fingers both ways? Don't tell me. I don't want to see it. There are those people, right? So this rule is not for them. That's why we really should have that probably would violate some kind of federal regulation to check if people are double jointed to, grant them permission to join a class, but,
Does that mean that we're essentially saying x is the z coordinate of vector c is in the positive direction?
You could, if we had a coordinate system set up, well, yeah, let me draw a picture like that. That's a good question. In terms of my other picture, now we can't assume, right? We can't assume a priori before the fact that the vectors that we're given are perpendicular. So the A and B vectors which are given, not necessarily perpendicular. They might just be like this, right? They might be like that. They might be like this. Who knows, all right? It doesn't matter. As long as they're not collinear, there's a plane in which they lie. And so that plane has a normal, which is a direction perpendicular to the plane, right? And we just have to pick what's the upside or the downside of the plane. No. So which one did you want me to put? Did you want me to put A in the x direction or the? Let's do that, right? So if this is A and this is B, right? And then I do the right-hand rule. So this means coming out of the board, right? So I point my right hand out of the board, I cross it into B, my thumb has to point up. So yeah, the Z would be the cross product direction. And this vector the notation that we're going to use for C is A cross B. Now I still haven't quite told you the description of it completely because there's something else. We had to fix the length of the cross product. How should we do that? Any ideas? What would be a natural thing to use for the length of the cross product?
A unit vector.
A unit vector. Well, that's true. You could write that as the magnitude of A cross B, whatever that is. That's my question, really. And then there's a unit vector. This is given by the right-hand rule that I've been just talking about. Or R. Sorry, I'm an idiot. But what should the magnitude of the cross product be? Yeah, it sure like this much should be true, right? If we doubled the length of A and kept B the same, it should double the magnitude, right? If we doubled the length of B and kept A the same, it should double this magnitude. So if you think about that, what would maybe that be? That could be the area of the parallelogram, which is defined by the vectors AB. That's what it's going to be. So this is going to be the area of parallelogram. I can't spell. I'll fit it in there. Here's the parallelogram. Goodness gracious, I give up. Anyway, so here's A, here's B. All right, like this, let's say. And then, of course, you can draw another copy of B over here, right? I tried. And you can draw another copy of A over here, up here like that, parallel to the other one, right? That resulting shape is a what? A parallelogram, right? What's the area of that parallelogram in terms of this angle here, theta? Can you guys tell me the area of the parallelogram?
Is it 1/2?
Oh, no, there's no 1/2 here. You're thinking trapezoid. But, and I only know that because I had a college algebra student come ask me about trapezoids yesterday. Otherwise, I would not have said that. Totally random. But anyway, if you look at this length is B, right? That's theta. This would be B sine theta. So that would be the height of the parallelogram. This distance down here, the base of this one as I've drawn it, would be A. So the area of the parallelogram would be what? A times B sine theta. That would be the height times the base. AB sine theta should be the area of the parallelogram. That should be the magnitude of the cross product by design. That's how we'll construct the cross product, all right? So, in short, this is what we want. We want A cross B to equal to AB sine theta. That is our other desire. All right, so this is on our wish list. So our wish list contains pretty much two things. One is that the direction of the cross product be given by the right-hand rule, all right? Number two, that the magnitude of the cross product be specified by that formula. Yep.
What's RHR?
Right-hand rule. Or RR. I'm sorry. No, I regret nothing. That's not entirely true. I regret talking about the dot product for 15 minutes. But I hope you guys got something out of that. All right, so what's the formula that does this? What satisfies these criteria? Here it is. This is the formula. So definition, A cross B is equal to, here we go, A2 B3 minus A3 B2, comma, A3 B1 minus A1 B3, comma, A1 B2 minus A2 B1. This formula you can memorize pretty easily, actually. There's like a really clear pattern here. Do you see the pattern? What we have is that the first component depends on 2 and 3. The second component depends on 1 and 3. The third component depends on 1 and 2, right? It's always the one that you're not at that is missing. It's wherever you're at is what's missing. 1 doesn't have 1, 2 doesn't have 2, 3 doesn't have 3. See that? That's the pattern. And also, there is a cyclicity, if you will. So if you look at it, the pattern is like 1, 2, 3, 2, 3, 1, 3, 1, 2. These all get pluses, right? And if you look at the pattern, and I'll kind of elaborate, if we have the pattern 3, 2, 1, or 2, 1, 3, or 1, 3, 2, they all get minuses. And what I'm talking about is what? Let me try to zoom more in on the pattern I'm talking about. So like, let's see here if I can tell you what I mean. This 3, 2, I'm talking about this 3, 2 here. This 1, 3, I'm talking about this 1, 3. This 2, 1, I'm talking about this 2, 1. Those are the minuses. That's the pattern. What are the pluses? See the other ones? The pluses, 2, 3, that's this guy, right? 1, 3, 3, 1 rather, is this one. And 1, 2 is this one. That's the pattern. Now, let me just tell you, there's like a really slick, simplified formula for this. And here's what it is. That's equal to the sum over I, j, and k equals 1 to 3 of epsilon I, j, k, a sub I, b sub j, x hat sub k. That's just a stone cold formula for the cross product. What is this epsilon thing? That's just a symbol, so-called Levi-Civita symbol. Or sometimes it's just called the antisymmetric symbol. And the way it works is that epsilon 1, 2, 3 is equal to epsilon 2, 3, 1 is equal to epsilon 3, 1, 2 is equal to 1. And on the other hand, epsilon 3, 2, 1 is equal to epsilon 2, 1, 3 is equal to epsilon 1, 3, 2 is equal to minus 1. If you have a symbol with 3 indices, which can range over 3 values each, how many total values do you have in principle? 3 times 3 times 3, right? That's how many? That's 27 possible arrangements of 1, 2, and 3, right? Of those 27 possible arrangements, 6 are non-zero that I've written on the board. All the rest of them are defined to be 0. That's what this formula does for you. It just keeps the 6 non-trivial terms which define the cross product. That's it. I personally think this is the right way to do it. However, every calculus book known to mankind and most of the engineering books you'll ever read define the cross product in terms of a quote-unquote determinant formula. All right? And that also has a place, so let me talk about it. This is equivalent to writing the determinant of x hat, y hat, z hat, A1, A2, A3, B1, B2, B3, like this. This is the so-called determinant mnemonic, if you like. If you're going to prove something about the cross product, this is way easier, right? If you have this memorized, it's as fast as this. However, when I'm sleepy and I fall into my old habits, I use the determinant myself, I'll admit it. However, if I'm sleepy and I calculate a cross product, there's about a 40% chance I got it wrong. It is imperative that you check your answer here. We're talking about 6 products, right? 6 different products, like at least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 identifications of numbers being what you think they are. 12 identifications, 6 products. That's at least 18 possibilities for making a mistake arithmetically. The odds are high you're going to make a calculational mistake calculating the cross product. You need to check your work every time. How do you do that? Go back to basics, right? The dot product of A and B has to be 0 for the cross product. Calculating dot products is easy. It's easy to check your work. So do it, right? Don't just throw points away on the cross product problem. Just get it right, right? If you get it wrong, don't despair, just go back. You made one arithmetic mistake somewhere. You probably can see what it is in retrospect as you look at it. Let's do some. So example 2. Suppose I have 1, 2, 3, and that's my A, and I have B is equal to, let's do 0, 4, 5, all right? Let's calculate A cross B. By the way, as I'm doing this, question to think about. Oh, thanks. Is it at all obvious that this definition I wrote down satisfies these criteria? It is not obvious, but it's true. I will show you the proof in time, but let's calculate some first. So you guys, how do you want me to do this? What method would you like me to use? Tell me, let me exhibit the determinant thing. So determinant x hat, y hat, z hat, 1, 2, 3. I mean, I will say this, doing the determinant here at least gets you some prep for Math 221 where you're going to calculate determinants in there. Now, or if you've already had Math 221, then you already know determinants. Wait a minute, can you take 221 before 321? What's the?
You have to take 221 first, as of now.
Before 320? No, not, my bad. 231, this course. Do you have to, 221 is not a prereq for this, just Calc 2, right? So some of you are currently taking Math 221? Is that right? Yeah, but you have not, obviously you haven't done this yet. This is later in the course. So, hooray. All right. It's one of those, you know, I think I had one semester where I covered the exponential, like exponential growth in like 3 separate classes. It was like my semester of exponential growth. I got it in chemistry, I got it in physics, and I also got it in calculus. Like all 3 covered this stupid exponential growth. All right, anyway, so x hat times the determinant. So this is what's called the expansion by minors. If you want to have fun, you can like go to Dr. Skimbortis and like tell him that you think that this formula for the determinant and the cross product is like a really solid logical formula, and it's really the way to write things, and just like praise the formula and then see what happens. Okay, that's actually really bad life advice, but no, I mean the thing is this formula is it's a chimera, it's a hybrid. It's not quite right because we take the determinant in Math 221 of matrices, and a matrix is not something that's got a vector in the first row, not just a vector, 3 vectors. And then the second 2 rows are numbers. That's not what a matrix is. A matrix is a box of numbers, right? Well, that's one way to think of it. This is kind of 2/3 that, 1/3 not. So, yeah, I mean, people object in that regard. If you're a suitably advanced nerd, you can give this a context in which it's well defined. Who cares? You guys don't care about that. This formula, though, generalizes to n dimensions. I'll say that. So this is 10 minus 12 minus y hat. Look, so there's danger here, right? The danger is this minus y hat. It's mission critical that you get that minus there, right? That minus matters. And so here's 5 minus 0. And you guys, the things I'm writing in red, can you tell me how I'm doing it? All right, so let me give you something to hang your hat on here. A, B, C, D. Tell me what the determinant of A, B, C, D is.
A, B, minus C, or C, D.
Yeah. Multiplication commutes. For some reason, must write it BC. I can't explain it to you. It's how I'm wired. But anyway, there you go. This is the determinant of a 2x2 matrix. This is the pattern. So the determinant of a 3x3 matrix is the alternating sum of the I forget the name of these stupid things. This is quote unquote Laplace's expansion by minors. If you calculate a 4x4 determinant, it's an alternating sum, a plus minus sum of the determinant of 3x3 matrices, 3x3 submatrices, where the 3x3 submatrices are selected from everything you're not using, corresponding to each plus and minus. So, so to calculate a 3x3 matrix, we're talking about 6 total terms. A 4x4 matrix actually has 4 factorial. You guys learned that last semester. How many is 4 factorial?
24.
24. If you have a 5x5 matrix, we're talking about 120 terms. Determinants are bad. I mean, they're beastly, all right? But anyway, 3x3 for here. And what is this? Cleaning it up, I prefer the Langle-Wrangle notation, this angle bracket notation, -2. You don't see this in engineering as much, but that's just because they have a unhealthy need to pay homage to Hamilton, who's long since dead. You know, this quaternion notation, but -2, -5, 4. All right, now let's hope I made a mistake. Did I make a mistake? Let's find out. What is A dot A cross B? What's that equal to? It better be 0, right? We've got 1 times -2 plus 2 times -5 plus 3 times 4. And what's B dot A cross B? How's that go? 0 times -2 plus 4 times -5 plus 5 times 4. I'll admit it. A lot of times I just check one of them being perpendicular. It's true. It's not ideal though. I mean, you really should check both, but usually if you check one, it suffices in my experience. You have to get pretty unlucky to get an example where you get one of them to be 0, but the other one not 0. Okay, so what then? Is that 0? I can't do math. Oh yeah, -12 plus 12, 0. And -20 plus 20, 0. Hooray! We can answer other questions now, right? Like, for example, if I have, this is A, and this is B, right? And I ask you, what's the area, if I connect these like so, and shade that area in, what's the area of that triangle? You say it's half of a parallelogram. Do you guys, everybody else see why that is? If we just put A up here again, right? And we put B over there again, then the green shaded region would be this same area as the red shaded region, right? And by symmetry they're equal. So the area of the triangle, should be 1/2 the magnitude of A cross B. Now what is the magnitude of A cross B? AB sine theta, you're not wrong, but do we know theta? We don't, right? So we do have A cross B right here, right? So what's the length of A cross B? One of these markers is bad. That one? Nah, they're all bad. Square root of what? 45, so that's 4 plus 25 plus 16, right? Which you say is 45?
Yeah.
Cool. And then, of course, we got 45 over 2, right? So, yeah, square root of 45 over 2, which, of course, is equal to the square root of 5, right?
No, what?
We just took 4.
No.
No? Oh, okay. I mean, so that's the square root of 45 over 4, all right? And then you just cancel the 4s, and you get 5. No?
Yeah, we'll go with that.
Yeah, I mean, come on. It's just like if you have, 64 over 16, you cancel the 6s, and you get 4.
Yeah. I like it.
No?
Checks out. Checks out.
Hopefully you don't believe me. This is a higher stakes game to play in college algebra. Because some subset of them
Percentage of the
might believe. Yeah. So let me erase the evidence. All right. It's fun to collect those things. Someone should write a book full of just that. It's probably been done. All right, anyway. Okay, so there we go. The area of that triangle in 3 dimensions, sitting somewhere in space, is this, all right? The area of the parallelogram formed by A and B is square root of 45, all right? Let's see here, what else can I tell you? Now, so if you look at this and this, you could have also produced these numbers just by straight with my first formula, all right? Like that would have also been totally fine way to do it. There's another way of doing cross products where you just put the vector one on top of the other and like make lines, but I don't know that thing off the top of my head, so let me not try to tell you because I'll mess it up, all right? But there is like a nice like slick notation where you don't even bother writing the x hat, y hat, z hat. You just write the 2 vectors and like just see the pattern. I'm not too fussy about like what you write to do the cross product, but I do insist that the answer be written in correct mathematical notation, right? So like it needs to be a vector, just like the dot product needs to not be a vector, right? The dot product is a number. If you write the dot product as a vector, that means you still have studying left to do, all right? Like you're not done. All right, so let me show you why the formula is what it is. Now, I haven't verified that it satisfies the right-hand rule, right? But you can check that out pretty easily by looking at unit vectors. So while I'm, whoa, a little tiny. So I would encourage you just to think about it for a second here. If we have, for example, x hat cross y hat, right? That would be 1, 0, 0 crossed with 0, 1, 0. And if you go through the formula that I gave you, what you get is 0, 0, 1, which of course is z hat. And likewise, you can check that y hat cross z hat is equal to x hat. You can check z hat cross x hat is equal to y hat. And you can remember all of these things with like a circle of cross productness. Or some people use a line that doesn't end, it just keeps going. But the way the circle works is if you go clockwise, as I've written it, that describes this formula. X cross y is z hat, z cross x is y hat, right? What else? What I miss out? Oh yeah, y cross z is x hat. If you go the other way, you get minuses, all right? And we can also use these alone to calculate cross products. So where am I? Example 3. I'll do a really simple one here because this technology is how you do really simple examples. So like if I had, for example, A is equal to x hat, and I had B was equal to, oh, I don't know, 0, 2, 3, all right? This is an ideal opportunity to not use the determinant formula. The determinant formula is the bad choice here. Hand-to-hand algebra is the better choice. What I mean by that is A cross B is what? It's x hat crossed with what? Well, this is 2y hat plus 3z hat. And while I haven't proven the formulas yet to you, the cross product has pretty much all of the formulas that are true for the dot product in the terms of the algebra. Like it's got a distributive property, you can pull scalars through, but there's one wrinkle. The cross product is not commutative, all right? A cross B is minus B cross A, that is true. You gotta watch out for that. More on that as we go on here. So we get 2 x hat cross y hat plus 3 x hat cross z hat. What is x hat cross y hat? Well, it's z hat. So I got 2z hat. How about x cross z? Check it out. X cross z goes counter the circle, so we get minus y hat. So minus 3y hat. And if I go back to my Langle-Rangle notation, my angle bracket notation, that is what you got here. You got 0, minus 3, 2. There you go. That's your cross product of A and B. Is that perpendicular to these two vectors? Check it out. X hat dot this, 0. B dot that is minus 6 plus 6, otherwise known as 0. All right, we're good. So these are the two main methods of calculation for cross product, all right? You need to, practice about 10 of these until you're like really solid at least. Here is, let's see here. Yep.
Unlike a test or something, do you care which way we use the cross product? Like, because you gave us 3 definitions, do you care which one we use?
You should use the right one for the job. On the test, if I ask a question on the test which involves the Levi-Civita symbol, then that would be like a bonus question. So that is outside the proper margins of this course by some estimates, but I teach it to you because it was not taught to me, and it actually is kind of important for higher level engineering to at least be exposed to it, all right, that formula. But anyways, so in short, whichever you want is fine. But so here are some. These are the more serious identities for the cross product. I think I have a text box with the less serious ones, like the additive one. But we're almost out of time, so let me just focus on this one. The cross product is not associative. So if you put the parentheses here versus putting the parentheses there, it doesn't give you the same result. All right, it's like subtraction. It's not an associative operation. It does satisfy the so-called Jacobi identity, all right, which is kind of a measure of how far it departs from associativity. And it also has this cyclicity property, which is that if you take A dot B cross C, it's the same as B dot C cross A, it's the same as C dot A cross B. That's that pattern, that 1, 2, 3 pattern we were seeing, 1, 2, 3, 2, 3, 1, 3, 1, 2 pattern, yeah? And then most interestingly to us, Lagrange's identity, which is this. If I was a more draconian professor, I would have assigned you Lagrange's identity as a homework problem. It is non-trivial. Here's the proof of Lagrange's identity. Using the epsilon symbol and the fact that when you contract a pair of epsilon symbols, you get this anti-symmetrized difference of Kronecker deltas. Anyway, long story short, cool things happen, and you end up with the magnitude of the cross product squared is the product of the magnitude squared minus the dot product squared, right? But last time from law of cosines, we proved that A dot B was AB cosine theta, right? So if you square that, you get product of magnitude squared on both terms, and then you can factor that out, and you've got that times 1 minus cosine squared. But we all know 1 minus cosine squared is sine squared. And so that gives us that the product of A cross B, as we defined it in terms of that ugly formula, is equal to AB sine theta magnitude. But it is a non-trivial. It's much deeper than I think the oh man, the cross product identity. And you guys have a question? Do I not have like? Well, anyway, we're out of time for today, so pick up again tomorrow here. Sorry, I did not get to the formula for a line and plane yet. My bad. I think I'm supposed to give a quiz tomorrow. Is that right?